Hello, my 20-1 friends. Okay, so today begins the second last lesson of our unit on absolute value functions and reciprocal functions. And so far, we've spent 3 lessons talking about absolute value functions. We've talked about linear absolute value functions, quadratic absolute value functions, and then solving absolute value equations. Okay, in these last 2 lessons, we turn our attention to the other portion of the unit, which is on reciprocal functions. Now, we've seen the word reciprocal before. Actually, the first time it was probably introduced to you was with a negative exponent, right? We talk about when we have a negative exponent, we flip the base, right? So 3 to the negative 2 is the same as 1 over 3 to the 2. Okay, that was one instance where you've heard the word reciprocal. Another one was with perpendicular lines. Okay, we talked about slopes of perpendicular lines being the negative reciprocals of each other. Okay, so in that sense, if I had a slope of 2 over 3, the negative reciprocal of that would be negative 3 over 2, and we flip the 2 over 3 to be 3 over 2. The final context where you probably would have talked about reciprocals is actually with dividing fractions, okay? When we're dividing fractions, we say that we can multiply by the reciprocal of the second fraction. So if I had 1/3 divided by 4 over 3, I can change that to 1/3 times the reciprocal of 4 over 3, which is 3 over 4, okay? So essentially, the reciprocal just means we're flipping something, okay? And so if I had a 4, you want to think about that as a 4 over 1. And if I was to flip it, that would be a 1 over 4 now. Okay, so now what we want to do today is we actually want to look at equations of lines. So y equals mx plus b. We did all that through grade 10, right? Y equals mx plus b. So m is going to be your slope and b is going to be your y-intercept, and that would create a straight line. Now we're going to take that a step further and we're going to graph y equals 1 over mx plus b and see what that looks like, okay? So that's where we're going today, and then tomorrow will be quadratic functions, and then that will wrap up this unit, okay? Okay, so let's get started. And the first thing I want to do is we're just going to play around with the table of values for a second. We're going to play with the equation y equals x plus 1. And y equals x or y equals 1 over x plus 1, sorry. Okay, I'm just going to hide my face for a sec so you can see the question at home. Let's sketch the graph of a function with its reciprocal function. So we're going to use y equals x plus 1 with y equals 1 over x plus 1. Complete the table of values below. Try not to use your calculator. Make your math teacher happy. See if you can do this in your head. Okay, so I'm just going to go through the first row first. So we're just going to plug in negative 10 for x. We're going to plug in negative 5 for x. We're going to plug in negative 3 for x. Okay. You can pause me and try and fill that row in yourself before I show you the answers. But essentially, negative x plus 1 is negative 9, right? Negative 5 plus 1 is negative 4. Negative 3 plus 1, you can do that, right? Okay. Think about it when you get fractions here. This is negative 3 over 2. If I want to add 1, just call that 2 over 2. So that would be negative 1 over 2. Okay, that's not as scary as it looks. All right, so you should have this guy for your first row. Now, in the second row, here's what I want you to notice. You're going to get, if I plug in negative 10 in for x, I'm going to get negative 9, but now instead of saying negative 9, it's going to say 1 over negative 9 because x plus 1 is on the bottom. So essentially, I'm just going to take each of the x values that I see here. Sorry, I shouldn't have said x values. Each of the y values that I see here, and I literally just have to take the reciprocal. So this is now going to be negative 1 over 9. This guy will be negative 1 over 4. This guy will be negative 1 over 2. So fill that row in. You can pause me for a sec to give yourself some time. Yourself some time. You-self. I don't know what I'm talking about. That's why you don't want me to teach you English. Okay, this is what you should have. Okay, negative 1 over 9, negative 1 over 4. The only thing I want to kind of talk about right off the bat here is this guy. Because the y value was 0, you ended up with like the y value is 0 on your original guy, right? The y equals x plus 1. That's going to give me 1 over 0 in the reciprocal function. I can't divide by 0, right? We talked about that with our rational unit. We can't have 0 on the denominator. And so that actually nothing would exist there. Okay, so D and E is just my quick way of saying does not exist there because I didn't have a whole lot of room in the table. Okay, so now what we want to do is we want to try and graph the reciprocal function. I'm not worried about you graphing the line right now, but we are going to try and graph the reciprocal function. Things that I want you to think about right off the bat is that D and E, that denominator of 0, that's going to create a vertical asymptote. Okay, so see if you can plot these points. So we're looking at like when x is -10, y is -1 over 9. When x is -5, y is -1 over 4. When x is -3, y is -1 over 2. When x is -2, y is -1, and so on. Okay. Okay, here's the graph that you should have gotten. I did graph both for you. So the purple guy is the x plus 1, y equals x plus 1, and then the green guy, the green graph, is the 1 over x plus 1. Okay. So just take a look at yours, compare it to mine, make sure everything's cool. And now we're just going to answer a few questions on it, okay? All right, so for the graph of y equals 1 over x plus 1, what happened when x equals -1? Well, when x equals -1, right here, we ended up with a vertical asymptote, okay? And the reason was because our denominator had a division, or our denominator had 0 there, so we can't divide by 0, okay? What did the y values do as we approached x equals -1 from the left? So if I'm approaching x equals -1 from the left, what that essentially means is here's my target, here's my target, x equals -1, okay? If I'm approaching from the left, that means I'm coming this way. Well, what's happening to my y values is my y values are shooting down to -infinity, okay? Y values are shooting down to -infinity. So the way we say that is the y values approached -infinity. Okay. Now, what happens, or what did the y values do as we approached x equals -1 from the right? I'm just going to hide myself for a second so that I can talk to you about that. Again, our target is this -1. I'll put it in the right spot this time. And now we're approaching it from the right. So I'm heading this way, approaching -1. What's happening is that our y values are shooting up to +infinity, okay? Y values are shooting up to +infinity, okay? That, by the way, speaks of a vertical asymptote, okay? When we see the x values approaching a particular number and the y values going to positive or negative infinity. So those y values either shooting way up or shooting way down, doesn't really matter whether it's positive or negative. That mathematically defines, hey, I've come to a vertical asymptote. My graph is bending towards that asymptote and is going to go closer and closer and closer to that asymptote, but never actually touch it, okay? Awesome. So, what happened as the x values went to +infinity? Well, again, I'm just going to hide myself for a second so I can draw that out for you. As the x values are going to +infinity, now I'm going that way, right? Well, you can see that that y value seems to be leveling off. And what it's doing is it's actually approaching 0, okay? It's approaching 0. And if you don't believe me, take your graphing calculator, put this in your graphing calculator, and just start tracing that line all the way through. You'll see that the y values are getting smaller and smaller and smaller and smaller and smaller, but they'll never ever hit 0, okay? And so we say as x approaches infinity, y approaches 0. That arrow here, contextually, that's mathematical shorthand for approaches. So as x approaches infinity, y approaches 0. Okay. What happened as the x values went to -infinity? So similar conversation. Now I'm heading in this direction. I'm going to -infinity. Again, they're rising, 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 but they're leveling off. Okay. And they also are approaching 0. So we would say as x approaches -infinity, y approaches 0. That speaks of something called a horizontal asymptote, okay? The horizontal asymptote is the horizontal line that a graph will forever approach but never actually hit, just like a vertical asymptote is a vertical line that the graph will forever approach but never hit, okay? Were there any points that were the same on both graphs? What were these points, or why were these points the same? Okay, and we can see actually 2 points that ended up being the same on the graph. I'm just going to hide myself for a second. This point right here and this point right here. And the trick in these points is actually the y value of -1 and 1. Okay, we had y values of -1 and 1 there. Those points stayed the same. Well, why did those points stay the same? Because when I'm taking the reciprocal function, I'm flipping all the y's, right? Remember our table of values. That -9 became -1/9. That negative, I don't remember the points I gave you, but that -1/2 would have become -2, okay? So when I flip 1, I get 1/1, which is still 1. When I flip -1, I get -1/1, which is still 1. Okay, so those are called invariant points. And I know we've used that term before. Remember that invariant points are points that remain unaltered when I do something to the equation. So it's at y equals ±1. This is because the reciprocal of 1 is 1 and the reciprocal of -1 is -1, okay? Okay, so what is the domain? For the domain, we can be anything we want except where that vertical asymptote is. So we say x is a member of the reals, but x can't be -1. And then for the range, we say same thing. It can be anything I want except for the horizontal asymptote, which is at y equals 0. So we would say y can be anything we want, a member of the reals, except y can't be 0. Okay, awesome. So just to summarize where we've been so far, if y equals f of x, then its reciprocal function is y equals 1 over f of x. You have to fill in the f of x in your workbook there, where f of x can't be 0. That is, the point x comma y is on the graph of y equals f of x. Then x comma 1 over y is on the graph of y equals 1 over f of x. Essentially what we're doing is x's don't change, y's do change, they become the reciprocal. Okay, so that is to say the x values don't change and the y values do change. Okay, don't touch the x values. The x values will remain the same. Horizontal asymptote, a line that the graph approaches as x approaches positive or negative infinity. So as x approaches infinity. For now, the horizontal asymptote will always occur at the x-axis or the line y equals 0. A horizontal asymptote occurs when the x values of a function get increasingly large and the y values begin to converge to a particular value, okay? This value in 20-1 will always be 0, but next year it will vary, okay? In 30-1, we'll talk about horizontal asymptotes in different spots, but for 20-1, we're gonna keep it at y equals 0, okay? All right, and then vertical asymptotes will occur at the non-permissible values of the function. The vertical asymptotes will occur at the x-intercepts of the original function because the y value there is 0 and I can't reciprocate 0. Okay, I can't take the reciprocal of 0, that would be undefined. As the x values approach the vertical asymptote, the y values grow without bound. Okay, that is the y values go to infinity. Whether that's positive infinity or negative infinity doesn't change the fact that it's a vertical asymptote. Okay, awesome. Never use an abbreviation such as HA or VA on a test, and especially not on your diploma, okay? That's super important. You always use full words, full communication on any written assessment, okay? All right, so let's practice a few questions together just to get you nice and comfy. Okay, so we're going to sketch the graph of y equals 1 over 3x plus 9, but we're going to do so by first sketching the graph of y equals 3x plus 9. We're going to start with something that's kind of familiar to us, okay? State the domain, range, and equations of asymptotes for y equals 1 over 3x plus 9. I'm just going to hide my face there for a sec so you can see the question at home, okay? And so now what we're going to do is we're going to start by graphing y equals 3x plus 9. Well, there's lots of things I know about that graph already, right? I know that I have a y-intercept at 9. I know that my x-intercept, I could plug in 0 for y, bring the 9 over, that'd be -9 equals 3x, and then divide by 3. And so I'd have an x-intercept at -3, 0. So I know that I can put a point here at 0, 9. I can put a point here at 3, 0, and I can connect that line. I can connect those dots into a line, okay? So here's my line, y equals 3x plus 9. Now, when I go to do the reciprocal, okay, there are a few ways to do this. I'm going to kind of talk about what I think is the easiest way to look at it. Remember that essentially you're going to go along the x and you're going to reciprocate all the y's, okay? But there's certain points that matter more than other points in one sense of the word to help you with the diagram, okay? So the first thing I'm going to think about is right at this x-intercept here, I know that at the x-intercept, I'm going to get a vertical asymptote, okay? So I know that I'm going to have a vertical asymptote at x equals -3. I know that I'm going to have a horizontal asymptote at y equals 0, right? So I can put those asymptotes in right away. When you go to put asymptotes in, and you should draw them in, okay? When you go to put them in, they should always be drawn as dotted lines because they don't actually exist as part of the function. We're using them to help us shape the function, and they dictate the shape of a function, but they are not part of the actual function, and that's why we have to draw them as dotted lines, okay? Now, the next points that we want to talk about is where y equals 1 and when y equals -1. I know that those guys there are invariant points, okay? So when y equals 1, right where the original graph was, I put a dot there because I know that that will stay as a dot. And when y equals -1, I put a dot there because I know that that will stay. Now, the last thing to consider is the reciprocal function always goes in the opposite order. So in this little section here, I'm increasing. So my reciprocal function needs to decrease and it needs to ride along these asymptotes. Well, the only way to do that is to have a shape that looks something like that. Okay, here I'm also increasing. So my reciprocal function needs to be decreasing and I need to be riding along the asymptotes. And so it's going to end up being like that. Now I'm drawing this with a mouse and so I'm not doing a great job of it. But what you want to be careful of in your drawing is don't show me something that looks like that. Okay, don't, like I mean down here, don't wave this. Okay, my hand was a little shaky because I'm dealing with a mouse. You doing it with a pencil, holding in your hand, you'll be able to do it much better. Okay, so this is roughly what you should have. I've got my horizontal and vertical asymptotes in, and then you can see the invariant point at y equals -1 and at y equals 1. And then I'm decreasing and I'm decreasing on this section as well. Okay, then it said state the domain, the range, and the equations of the asymptote. So for this guy, the domain is real, except that I can't be -3. So I say all the real family, but x can't be -3. And then for the range, member of the real family, but y can't be 0. Then I have asymptotes. You need to label the asymptotes. You can't just tell me the equations of the asymptotes. You have to tell me which one's vertical, which one is horizontal. Make sure you know how to spell the word asymptote. Okay, that's kind of important. So I have a vertical asymptote at x equals -3. Super important. I get lots of kids who try to tell me on a test, oh, I have a vertical asymptote at -3. That's not good enough. It has to be an actual equation. So any vertical line is x equals a particular number. So you'd say vertical asymptote at x equals -3. I need that whole statement, okay? Horizontal asymptote at y equals 0. Same conversation there, okay? You can't just say horizontal asymptote at 0. It has to be horizontal asymptote at y equals 0, okay? Awesome. Okay, we're going to try another one. This time we're going to try y equals 1 over x minus 5. And we're going to do the same thing. We're going to sketch the graph of y equals x minus 5 first. We'll think about domains. We'll think about ranges of the reciprocal graph once we get there. And we'll write the equation of the asymptotes for the reciprocal graphs as well. Okay, but let's start with y equals x minus 5. I know I have a y-intercept at -5. I know that if I plug 0 in for x, I would have that y-intercept of -5. I know if I plug 0 in for y, I'd end up with an x-intercept. That's a 0 equals x minus 5. So I'd have an x-intercept at 5. Okay, so I have a y-intercept at -0, -5, x-intercept at 5, 0. Sorry, that's a typo. That should say 5, 0. Let's just change that together. Okay, I copied and pasted it from my previous example. Okay, so I know I've got -5 here. I've got 5 here. That's enough for me to draw in my line. Okay, and so that should look like this. Now I'm going to have that same conversation I just had with you about how to draw these things. First guy is my asymptotes. I know I have a vertical asymptote where it hits the original guy hits the x-axis. Okay, so I have a vertical asymptote at x equals 5. I have a horizontal asymptote at y equals 0. So I'm putting dotted lines in. Then I'm going to mark my invariant points. I've got y equals 1 as an invariant point, so that'll be right there. And I've got y equals -1 as an invariant point, so that'll be right there. Okay, this function is increasing, and so mine needs to decrease. So mine's going to look something like that. And then over on this section, the original function was increasing, so I'm going to be decreasing. And so I'll look something like that. Now, I was actually decent with that. My hand wasn't as shaky as the first time I did this video. Yay. Maybe the coffee's getting out of my system or something. I don't know. But that's roughly what it should look like. Okay, so now I'll give you a computer-generated version of the same thing. Okay, and we'll talk about the domain, the range, and the equations of the asymptotes. For this guy, the domain will be x is a member of the reals, except it can't be +5. For the range, y is a member of the reals, but it can't be 0. Okay, and then for the asymptotes, I have a vertical asymptote at x equals 5. I have a horizontal asymptote at y equals 0. Okay, awesome. All right, the last question we'll talk about today. Given the graph of y equals 1 over f of x, determine the equation of y equals f of x. So now we're going backwards. I actually gave you the reciprocal function. I want you to come up with the linear function that would have created this reciprocal function, okay? I'm just going to hide my head for a quick second for those of you who are at home and need to see the question, okay? All right, so here's what we're going to do. Right off the bat, I can see that I've got an asymptote at x equals 7. Do you see that there? Okay. And so I know that that would have been an original x-intercept. I also know that my invariant points are at y equals 1 and y equals -1. So I know that this point wouldn't have changed. And I know that this point wouldn't have changed. Now look at that. I can actually draw a line right in there. Let me just get my straight line tool here. I can draw a line right in there that will pass through all those points. So I know that that is the equation of my line. Okay, again, I just want to make sure you're cool with what I did. I'm going to go where my vertical asymptote is will become the x-intercept. I'm just moving everything backwards. And then my invariant points are at y equals 1 and y equals -1. And that got me my 3 dots, and I knew this would be a line. Okay, so now I have to figure out the equation of this line. Okay, I know I have a slope of 1 here. Is that cool? Now I just have to kind of keep going and see where I would cross the y-axis. So that right here would be at -5. If you can follow me on that, then this would be -6 here. And then this would actually end up being, I can't get down there for you, but that would have ended up being -7. Okay, so I know that I have a y-intercept of -7 and a slope of 1. So here's what my line looks like. I'm just going to review this again with my notes. Vertical asymptote is at x equals 7, so this would be my original x-intercept. The points where y equals 1 and y equals -1 will be invariant. This gives us 3 points on our line, and so now I have that line. I've discussed that I have a slope of 1 and a y-intercept at -7. And so that would be the equation y equals x minus 7. Okay, y equals x minus 7. That would have been my original f of x. Okay, awesome. All right, so that's what we're going to do for today. Tomorrow we'll focus on quadratic reciprocal functions. I've listed your homework here. Take your time to go through them. And if you have any questions, please make sure you connect with me. You got this, guys. We'll see you soon. Bye-bye.